Aleksei, we can see you and hear you now, so please take it away. We will have to save questions for maybe doing it online. I think Aleksei will be able to answer them on Discord. So please take it away when you're ready.
Okay, yeah, I'm ready. Thank you. Yeah, hello everyone. First of all, I want to appreciate the opportunity to present remotely, and big thanks to organizing for putting an effort into this. And yeah, I'm sorry to cause so much trouble with setting up the remote presentation. Yeah, I didn't get my visa, so I couldn't attend the workshop in person. My name is Aleksei, and I'm doing my PhD at the University of Birmingham, and I'll present a joint work with Dan Ghica and with Barrett on something we called Equivalence Hypergraphs, or E-hypergraphs, which are a generalization of the graphs for monoidal theories. I want to highlight that the work is purely theoretical, and therefore don't expect any experiments or implementation or benchmarks, but I hope the work will be insightful and can foster some discussion. So we have essentially built some theoretical constructions, and that'll try and show what connections these constructions have with EGRAPHS and why would anyone be interested in these constructions. So first, I recall that EGRAPHS are primarily used for so-called algebraic theories, and I will explain what these are. Then I will explain what monoidal theories are and why would anyone be interested in monoidal theories, and hence why would anyone need EGRAPHS for monoidal theories. Then I will sketch why EGRAPHS, what troubles EGRAPHS face when someone tries to apply them to monoidal theories, and show how string diagrams can rectify this. Then I will very briefly and informally explain the underlying theory of graphs for monoidal theory that we have constructed, and I will demonstrate two examples. One example is about showing that EGRAPHS are a special case of our construction for Cartesian monoidal theories, and another example is something to do with how E-hypergraphs can facilitate the support for binding, like for example, lambda calculus. So traditionally, EGRAPHS are used for theories over algebraic signatures with a single sort of composition, which is just a function composition of a function application, sorry. And a theory is just a set of terms with some equations, and a signature is a set of generators that you use to construct the terms in your theory. And a signature is called algebraic if the number of outputs for each generator is exactly 1. I will also refer to the number of outputs as a coarity. So you can consider an example of a theory of commutative monoids. The signature consists of multiplication and the unit. And I have explicitly annotated the number of inputs and outputs, so the arities and coarities of a generator. So the multiplication has the arity 2 and coarity 1, and the unit has the arity of 0 and coarity of 1. And the equations are just the standard commutativity, associativity, and unitality for commutative monoids. However, yeah, we don't have to restrict ourselves to only consider like series with coarities of 1, and a more general series arise when we consider like the interaction between processes and try to describe processes, for example. We need more general signatures when we need to consider quantum processes, for example. So in contrast, consider a coalgebraic signature that contains two types of identities, one with like arity of 0 and coarity of 0, the other with arity of 1 and coarity of 1. The other thing is a symmetry that swaps its inputs into the outputs, and the other two are co-multiplication and co-unit, because, well, I flipped the number of inputs and the outputs, so now the number of inputs co-multiplication is 1, the number of outputs is 2, and similarly for a unit. And also consider a family of terms such that every term is constructed from these generators above by combining them using sequential composition and parallel composition. sequential composition combines terms if their types kind of match, and the parallel composition can compose arbitrary terms. An example of a term that can be constructed from such algebraic signature is something like this, which is a parallel composition of two subterms, just a combination of multiplication, symmetry, identity, and union. However, unlike the algebraic theories, such theories that are built from algebraic signatures come with some built-in equations that are not induced by the domain of application of this theory. And these built-in equations are the laws of symmetric monodal category. Namely, these equations prescribe that both compositions are associative and the identities are left and right identity for the respective composition. And also it describes the relation between the symmetry and some other operators, and notably this equation here, the bifunctionality of the parallel composition. So a symmetric monodal theory or some signature, just a set of terms constructed of the symbols from the signature by using the parallel and sequential compositions, modeled by the equations above and possibly model some other equations that arise from the domain. So for example, the theory of commutative hominoids is the theory constructed from the mentioned signature plus the built-in equations and plus the equations below, which are, as before, are just the associativity, commutativity, and the unitality equations, but for hominoidal version of the operator. Such symmetric, and if we omit the symmetry generator, we end up with just a monoidal theory. Such a theory is just syntax, and it kind of generates a very simple free symmetric monoidal category, which is called a prop. So we can reason about such theories categorically. We can provide the semantics for a syntax by building a functor from this prop into some more interesting category, for example, into a category of vector spaces, which is, for example, the case for quantum computing. Typically, the target category. And if this functor has some nice properties, we can reason syntactically about some semantic things. And such theories, they crop up in various areas, including, as I mentioned, quantum computing. You can build quantum circuits using the generators, and by specifying some equations, you can get with particularly nice and small quantum circuits. You can also do pretty much the same in probabilistic programming. You can express lambda calculus using symmetric monodal theories, and you also can build up digital circuits, and by using equations, you can define the operational semantics for digital circuits. And once you have equations, you would clearly benefit from having quality saturation procedure for this. So, for example, you can, by saturating the set of terms, you can then extract the smallest circuit, either quantum or digital. It's probably, of course, it's possible to use the current formulation of graphs to encode such theories. For example, it's as this structure, where I've just specified the number of inputs for each generator. I will just use variables to refer to each input of the generator. However, because we have so many built-in laws in our theory, this approach doesn't scale very well. So consider an EGRAPH for the previous example. Like I said, I just use variables to refer to the input, and then I just use both compositions to combine the terms. And after we saturate the EGRAPHs with all the laws, I will saturate only with built-in laws. I will ignore the laws of the commutative hominoid. We end up with something like this, which was too big to fit into the slide, so I had to crop it. So, even though the number of E classes is not big. Each class just has too many terms to contain because of all the equations, we have so many ways to reassociate the expression, and also to we have the bifunctoriality, and we need to like switch. We can switch symmetry and so on. So a natural question to ask is whether we can somehow get rid of these equations, or rather like sweep them under the carpet somehow. Well, the spoiler is like, yes, we can. And here is how, this is where string diagrams come to rescue. And string diagrams are two-dimensional syntax for symmetric Monoidal theories, which represent equivalent classes of terms modular by those built-in equations. And string diagrams appear to be a convenient tool for graphical reasoning. They're built inductively using wires and boxes. So identities become just single wires, symmetries become like crossed wires, and the generator from the signature become boxes. And you can compose string diagrams sequentially and in parallel. And also, if you remember, we had the identity with subscript 0, which was the identity for the parallel composition that is just encoded as a blank space, which is very convenient. You don't have to draw it. And this notation, it absorbs some of the equations and of the laws of the monoidal category, and some other equations are absorbed because we treat string diagrams up to some topological deformations. So if you slide boxes along the wires or cross wires like twice, you stay with the same string diagram. In particular, note how bifunctoriality law gets absorbed by the notation. So, well, the dashed red and blue boxes are not part of the string diagram. They're just to demonstrate how you read the string diagram. So if you read it from left to right, you can derive the S sequentially composed with T and composed in parallel with sequential compositions of U and V. And if you read it from top to bottom, you get the parallel composition of S and U composed in sequence with T composed in parallel with V. But these two terms are represented by the same string diagram. And you can also encode some sort of structure in the monoidal theory by tweaking your topological of string diagrams. And another benefit of string diagrams is that they simplify the additional equations for which the term equivalent form is not immediately obvious. So this is the example of the Z-spider fusion rule for the ZX calculus, and because the ZX calculus is originally formulated in terms of string diagrams, it's much more convenient to use this kind of rules rather than not very obvious term equivalent, because we have here in this rule we have an arbitrary number of inputs and outputs. And another nice feature is that string diagrams can be represented combinatorially by hypergraphs with interfaces, where these built-in equations get completely absorbed by the notion of isomorphic hypergraphs. And we can perform diagrammatic training on string diagrams by doing graph rewriting on these concrete combinatorial structures. And that's how we can encode some additional equations from the monoidal theory by tweaking the definition of hypergraph and the isomorphism between them. So we can consider the previous example by now in its string diagrammatic form. So we encode the multiplication at the box with one input and two outputs, and we encode this co-unit by just dangling dot. And the string diagrammatic version of the first example becomes if you go on the right. And you can notice that it's already saturated with respect to all the built-in equations. I put this saturated bit in quotes because, well, we still have the naturality equation for the symmetry, so we can, because we can slide boxes along the wires, we can slide this dot along this wire and move it beyond the symmetry. But if we use the hypergraph representation of the same string diagram, we absorb this equation as well. So this particular example is like fully saturated with respect to all of the built-in equations. So here, the boxes of the string diagram became the hyperedges, and the wires became the vertices. And well, we need the interfaces to distinguish between the vertices, which are the inputs of the string diagrams, and the vertices, which are the outputs of the string diagram. So, well, once again, yes, we can get rid of these equations if we use hypergraphs, which are derived from string diagrams, which is nice. And, well, our work next form is EGRAPHS for symmetric monoidal that we use string diagrams for, well, in particular hypergraphs, as a representation for terms in a bottom-up manner with formalization from an SMT itself. So what we did is that we kind of extended the SMTs. So we introduced the notion of an enriched SMT where it added some generator plus, which allows us to take formal joins of several terms if they have the same type. So all of FIs should have the same number of inputs and the same number of outputs. And this formal join allow us to encode the equivalence classes. So we'll use this formal sum to express all of these terms are equivalent. And we will also extend the syntax of string diagrams to support such enriched symmetric monoidal theories by introducing these hierarchical boxes. And the dashed vertical lines will just like distinguish individual like equivalence components of this box. And much like in EGRAPHS, where we have a rule for congruence, so where like x equivalent to y implies that f of x is equivalent to f of y for some functional symbol f, we have a more general notion of congruence for our like string diagrams for terms, because just because we have two types of composition, parallel and sequential, and we encode these congruence conditions in string diagram forms as well as some of the properties of plus, namely its associativity, commutativity, and that it's an idempotent operator. So the set of equations look like this. So in particular, the topmost left one specifies this, well, intuitively that if G1 ... is equivalent to Gn, then the sequential composition of F with G1 is equivalent to, well, the sequential composition of F with G2 and so on, and F2 with Gn. And similar for the other rules, but just for other types of composition. And the bottom row prescribes that the plus is an associative, commutative, and idempotent operator, which keeps the set of terms with this operator with a structural semilattice. So the semantics of such an enriched SMT would be some category which is enriched like in the category of semilattices. So this class has some categorical semantics behind it. And by using these like classes and the extended string diagrammatic syntax, we can model the non-destructive feature of rewriting with EGRAPHS in the symmetric monoidal setting. So given a rewrite rule in string diagrammatic form from L to R and some sort of string diagram that can be read for the left-hand side of the rewrite rule, we can essentially first use the idempotence equation to duplicate the L, and then use the rewrite rule write one of the copies of L into R. And you can also notice that if we were to try to apply the same rewrite rule again, we would end up with 2 copies of R. And again, by using the idempotence equation, we can reduce 2 copies of R into 1 copy. So this form is kind of maximally compact and is saturated with respect to this rewrite rule. And such extended string diagrams have a concrete combinatorial representation, which we call E-hypergraphs with interfaces. So, well, in contrast with hypergraphs, E-hypergraphs can have also some hierarchical hyperedges that can contain arbitrary hypergraphs within it. So, for example, on the right, an E-hypergraph on the right represents the kind of this symmetry generator that was plunged into this hierarchical box. And we have slightly more complicated notion of interfaces just to be able to encode things that are within these hierarchical boxes. And notably, these concrete combinatorial structures, they absorb all the equations from all the laws of the symmetric monodal category, but they don't absorb the equations we have for L plus. So, in contrast to EGRAPHS, now, we model equivalence classes with these hierarchical edges, and unlike EGRAPHS, these equivalence classes now contain arbitrary equivalent hypergraphs rather than subtrees, which is obviously because we extended algebraic theories to monodal ones. And actually, the main technical result of our work is that such combinatorial structures are sound and complete for representing terms of extended symmetric monodal series. And once we have these E-hypergraphs, string diagrammatic reasoning becomes just E-hypergraph rewriting, which is formalized as a double push-out rewriting, which is a convenient framework to study properties of rewriting systems. For example, it's much more convenient to learn about confluence or applicability of parallel rewrite on these concrete combinatorial representations using double push-out rewriting rather than increasing about string diagrams. And like I said, this representation only absorbs the symmetric monodal category. And the first case study that I will show is that the plane EGRAPHS arise and restrict our enriched symmetric monodal series to Cartesian symmetric monodal series. That is series that come with 2 additional generators, the co-multiplication and co-unit, and I've just switched the inputs and outputs to follow the presentation of EGRAPHS. So the inputs flow from bottom to top. And there are also some equations that the generator should satisfy. The first bunch of equations are just the same equations that we had for commutative monoid. And the other 2 equations are just the naturality for this duplication generator and the deletion generator, so that we can copy things and we can delete things. And when we keep a symmetric monodal theory with such additional structure, it is essentially, such a theory becomes in a way algebraic. So we can assume that it only contains generators with co-arity of 1 without loss of generality. That's why it's kind of this is why EGRAPHS just arise as a special case of construction. And when I say that EGRAPHS are a special case, I mean that I need to mention that acyclic EGRAPHS are a special case of our construction. If you want want to support like EGRAPHS with cycles, we need to extend add some additional structure on the generator, but rather straightforward. So when I say that EGRAPHS for a special case, I mean that we can construct an equivalent E-hypergraph or rather a string diagram for any EGRAPH. And to illustrate how we can do it, just consider how any class gets translated into its string diagrammatic form. So on the left, we have any class that represent two terms, which are A times 2 and A bit shift 1. And each trivial E class gets translated as it is into a box launched into a hierarchical box. And what you can notice is that, well, now we have an explicit sharing of A by using the copy generator. However, the non-trivial E class is translated a bit differently. So similarly, we introduce a hierarchical box, but we supply it with an input for each input of the generators within the box, and we distinguish the components with the dash line. And we also supply the generators with additional deletion generators. And the intuition behind this is that, well, suppose from this representation, if we want to extract the A bit shift left 1, so we kind of replace this hierarchical box with its right hand side. So we end up with these two deletion generators and this bit shift, and then we just trace the inputs into, well, and then we just reconnect the wires with their respective ports. So we connect 2 with this one, which corresponds to this deletion. So, well, 2 gets deleted. Similarly, a copy of A gets deleted. Well, it's just applied to this input, and they're deleted because of the laws of the Cartesian structure. Well, and similarly, it's applied to this interface via this wire, and applied to the right interface of the bit shift through the wire. And, well, effectively, we end up with a bit shift 1. And, well, similarly, we can sketch like a general translation for arbitrary E classes. It just differs, well, it's just parameterized by the number of inputs, and yeah, by the number of inputs. Yeah, and, well, here is how we can like model not just E classes, but the evolution of EGRAPHS after we apply some rewrite rule and merge some E classes. So in the top figure, well, we had like some deletion, and then we want to apply the rewrite rule. We just replaces the multiplication with a bit shift, which is just like a classic example of EGRAPHS. And we can express this, well, this kind of life cycle of graphs by using string diagrammatic, and because we have like concrete combinatorial structures for these string diagrams, we can also express it as a concrete graph rewriting. So the first thing we do is we duplicate the tune by using the copy equation, and we do this to be able to identify the regex for the left-hand side of the rewrite rule. And then we apply this like non-destructive rewrite by replacing another copy of multiplication by a bit shift. And then to be able to compactly represent this structure, we need to factor things out. So we do this on the right, where we introduce dummy input that gets discarded, and by again using the equations for this formal join, we can factor out A2 like A1 and will achieve the same degree of sharing that we had for EGRAPHS. And obviously we can always construct such things. Well, these examples to the sanity check for our construction, and it also provides some categorical representation of EGRAPHS in terms of enriched, like simulative categories, in terms of category enriched over a category of similarities. And therefore, it also provides a possible framework for reasoning about EGRAPHS in terms of hypergraph rewriting. And another example I want to show is how string diagrams can facilitate the support for binding in different settings. And there is a classic fact that lambda calculus is a model for Cartesian closed symmetric monoidal theories. And in the example below, you can appreciate the benefits that string diagrams have. So compare the following two EGRAPHS for lambda calculus, where we have lambda abstraction, and the leftmost has explicit variable, and the second one uses indices. And the string diagrammatic version on the right uses bubbles to represent these bubbles to represent this lambda abstraction, and it uses wires to represent the binding. So, it means that string diagrams are automatically quotiented by alpha equivalence. So alpha equivalent terms just end up being the same string diagram. And you can also notice how the argument of the second lambda abstraction gets discarded. Thus, we can represent EGRAPHS for lambda calculus by using our construction applied to the Cartesian closed symmetric monoidal theory. So, if you consider an example of EGRAPHS for lambda calculus with explicit substitution, we just recursively, a single equation, which is a beta reduction, which is implemented in terms of explicit substitution, and the explicit substitution recursively apply the substitution to all the children E-classes. It's string diagrammatic construct within below, where bubble as before represent the lambda abstraction, and this grayish half circle represents the application of a lambda abstraction to its argument. And the nice feature of string diagrams for this Cartesian closed symmetric monoidal series is that the beta reduction is expressed just a single rewrite through string diagram. We just connect the wire of the argument with this dangling wire as the abstraction by discarding the application node and the bubble. So, once again, by applying this destructive by applying this rewrite non-destructively, we end up with something like this, and then we as well can factor things out to end up with pretty much the same thing we had in EGRAPHS. But I'd like to note that that Cartesian closed symmetric monoidal series have slightly more structure that can be directly derived from our construction. So just a sketch of how things could look like, and just further formalization of this construction is the future work. Yeah, because it has enough technical details to be a bit different from what we can do at the moment. We have presented generalization of EGRAPHS for symmetric monoidal theories, which could possibly broaden the area of application of EGRAPHS to quantum circuits, to probabilistic programming, or to digital circuits. I've seen quite a bit of of digital circuits talks on the program. And yeah, I think by just doing it from this theoretical perspective is just another way of doing it. I'm not like claiming that this is the right thing to do, but it's just, yeah, it just provides a different perspective on things. And these concepts can also like provide benefits for algebraic theories, which are already like efficiently supported by EGRAPHS by like teaching bindings in a nice way. And as well as by writing this theoretical construction, we automatically have a framework reasoning about graphs in terms of graph direction. Well, however, we didn't study like any like realization properties of each hypergraphs as like concrete data structure and formulate the corresponding quality iteration procedure. So hopefully this is something that we like discuss, and well, as well as the potential like practical value of this formalization. Yeah, you can also like find a link to a preprint, to just like, which is a link to a GitHub actually, but the archive version of the paper has like more elaborate details. Will be out on Tuesday, I think. And you can also find an email for, yeah, we are open to collaboration. So if you find this work interesting, feel free to get in touch. And I think, yeah, that's it. Thank you very much for listening.
Thank you, Aleksei, for the great talk. Unfortunately, we do not have time for questions since we are running over. The session resumes at 10:40, so everyone please head to break. Thanks so much.
Bye.